Hello dear colleagues, I'd like to represent our recent work, Particle Swarm Optimization based S-box generation. This article explores the computational particle swarm optimization method as applied to the problem of generating nonlinear substitution. We use nonlinearity, balance, delta uniformity, algebraic immunity, and linear redundancy as the main indicators, and randomly generated S-boxes are used as a set of particles. This article shows several PSO modifications for generating nonlinear substitution. Firstly, we reproduce the previous known PSO modification for generating S-boxes and show its low efficiency. Secondly, we propose our own PSO implementation and show that this method can actually generate substitution with high cryptographic properties. One of the basic primitive blocks of symmetric cryptography is nonlinear substitution. Nonlinearity, balance, delta uniformity, correlation, and algebraic immunity and other properties characterize the resistance of S-boxes to linear, differential, algebraic, and other cryptanalysis methods. Various methods are used to generate cryptographically strong substitution, so the idea of using PSO to generate S-boxes can be useful. The purpose of our article are researching of the PSO for heuristic generation of nonlinear substitution, experimental verification of the results, and justification of some PSO parameters to form S-boxes with required properties. Particle swarm optimization, heuristic method of global optimization. PSO is based on swarm intelligence, which is natural behavior of birds, fish, insects, and others. Swarm particles as a flyway fly together in search of food before they find a good place where the food is located. While searching for food, there is always one bird that has better information about the source of food than other. Since birds constantly share such good information in the search of process, the flock will eventually move to a better place where food is more likely to be found. In PSO, the movement of birds begins from one location to another, equivalent to a flock. Good information is equivalent to the most optimistic solution, and expected food is equivalent to the most optimistic solution for the entire algorithm. In the basic PSO algorithm, the population consists of n particles. The position of each particle in the swarm is influenced by both the most optimistic position during its movement and the position of the most optimal particle in its vicinity. The velocity and the position of each particle are determined at each step, as shown in formulas 1 and 2 on slide. Abstract 20 proposes interpretation of PSO for the generation of highly nonlinear S-boxes. Although the authors of this research make mistakes in calculating the nonlinearity of S-boxes, in particular see our commentary 13, we reproduced the proposed algorithm for computational search of nonlinear substitution and made our own research of the efficiency of PSO. Let's talk about PSO implementation to generate S-boxes from Article 20. S-boxes occurs using the algorithm shown on slide. Briefly, the S-box population is generated randomly, then the population of blocks is sorted in descending of nonlinearity. The velocity vector is updated by formula 1 and the location vector is updated by formula 2. The vector of the most optimistic position during the iteration p-best is updated for each generated population if the nonlinearity values of new blocks are better than previous ones. Then the special algorithm is used to preserve the b-activity. Next, the nonlinearity value is also calculated for all newly generated blocks, and all S-boxes, including those already in the population, are sorted again in descending of nonlinearity. N best blocks according to the nonlinearity remains in the population, all other blocks are discarded. The pseudocode of the algorithm you can find in an article. In this work, we propose a new implementation of PSO. The PSO method, modified by us, almost completely repeats the algorithm from Article 20. The difference in our algorithm is that on the step 3, when forming a new population, the first block of the new population is formed from interaction of the first block of the initial population with itself and changing a small number of values. This gives an almost zero velocity vector at the first iteration, which allows to gradually deteriorate at subsequent iterations. At subsequent iterations, if after applying this method the nonlinearity of this box is higher than 98, the blocks is thus mixed randomly to improve other parameters such as linear redundancy, delta uniformity, and algebraic immunity. At step 5, we use algorithms shown on slide to preserve the bijectivity. Step 6 is in both algorithms is the same. Further code of both algorithms from article 20 and our algorithm you can find in the article. Our proposed new modification of PSO allows to form as boxes with nonlinearity 104, delta uniformity 8, linear redundancy 0, and algebraic immunity 3 in a relatively short time. One of the following as boxes in decimal format is given on slide. The next step in our research was examination of the effect of particle population size and the number of iterations of the external cycle on the efficiency of heuristic generation of nonlinear substitutions. Results are shown on slide in the forms of histogram. As you can see, the larger n and max theta, the more blocks found. Detailed results you can find in the article. Finally, should mention that this work was supported in part by the National Research Foundation of Ukraine. Thank you for attention.